Evening, guys. Today's problem, we're going to look at a trig identity that's got some algebra in it, and we're also going to look at a different way of solving that trig identity problem using complex numbers for those who are interested. Okay, so the problem is, prove that these expressions here differ by a constant. What is the value of that constant? Think of it like sine squared plus cosine squared equals a constant. These things here differ by one. Alrighty. Solution. Some results that we're going to use. This is kind of like completing the square. A to the power of 4 plus b to the power of 4 is equal to that. And similarly, I could start off with a factored cubic. A cubed plus b cubed is equal to that. We've seen that before. And if I replace all the a's and b's with a squareds and b squareds, I get my power of 6, a to the power of 6 plus b to the power of 6 thing that I want. The reason I've done that is because we know that a and b are sine theta and cosine theta. Therefore, a squared plus b squared equals 1. That simplifies these guys down. Every time there's an a squared plus b squared, we just replace it with 1. Alrighty. Putting that into the problem I prepared earlier, there's too many symbols to write this all out. Left-hand side equals the difference between the values. Use those identities that we've just proven. Change the a squared plus b squared bits to 1. Do the identity again because we've got another a to the 4 plus b to the 4 part. Again, an a squared plus b squared equals 1. And then all your a's and b's cancel and you're left with just numbers, and the number is 112. On a side note, because the two expressions differ by a constant, that means that it's true for all values of theta. And if you graphed the function, it would just be a horizontal line. So you can choose any value of theta that you want to find the constant. You could put theta equals 0 into the expressions and find that the difference is 112. But we had to prove that it differed by a constant for all values of theta. And there it is. Okay, alternative working. If this seems confusing, then it's because we haven't done it this year. But hopefully for most of you who have done complex numbers, this all makes sense. Okay, if z is a complex number with a modulus of 1, and that's important, that's why it's in bold and underlined, then we can write z in polar form. We shorten it to cis theta. The conjugate is just cis of minus theta. Other useful results is if we take those complex numbers and multiply them together. If the modulus is 1, then we get the complex number times its conjugate equals 1, meaning that the conjugate's just the reciprocal. And then if we power a complex number using de Moivre's theorem, then there's a shortcut to it, and that's just cis n theta. And then lastly, the thing that's most important about this question is if we take the complex number and add its conjugate and then divide by 2, we get cosine. And if we take the complex number minus its conjugate, dividing by 2i, we get sine theta. Alrighty, so we can use that to actually form a trig identity, derive a trig identity. Cosine theta was equal to z plus its conjugate divided by 2. I factor out the half to the power of 4 expression, expand it using the binomial theorem. Going to get lots of simplification because the z cubed over z is z squared, and so on. Rewrite the 1 over z bits as conjugates, and then power them using the theorem that I referred to, and then adding complex numbers to their conjugates. We're going to get 2 times cosine theta, and we get that trig identity. So hopefully you can pause that and follow through with that. Similarly, expanding cosine to the 6 theta. You don't have to do all the working because you're just looking at the coefficients basically. You get that. Sine to the 4 theta. There was a division by 2i for sine, but 2i to the power of 4 is just 16. So we get this. Be careful where the minuses and the pluses go. It's a little bit not where you necessarily expect them to be. So we get this result. That's a trig identity for sine to the 4 theta. Proved all by complex numbers, which is cool. And the last one, there's a 2i to the power of 6 factor. That equals negative 1 over 64 when we power it by 6. Okay, and we get that last trig identity there. And then if we put it all together for the problem, find the difference between those two expressions, it simplifies heaps, and it actually simplifies to 112 as we expect. Your extension for today is to actually just solve it using the quick way. You may have already done this, and it's to use differentiation to prove the statement that the difference between the expressions is a constant.